My name is Michael Gaultois. I'm a researcher in chemistry, and I also have an office here in Maxwell. The type of research I do is trying to discover new materials that have better properties. The reason is because everyone wants better batteries and better solar cells, and that's what we try to do, is we take existing materials and figure out how to improve them, but also try to discover new materials with the properties that we want. So two of the things I'm doing now with Professor Claire Gray is working on materials that absorb carbon dioxide from coal-fired power plants. The reason that we're interested in doing that is just because there's a lot of them and they're going to be around for a long time. But also developing new battery technology, and that's important for sustainable energy, because if we want an electric grid, you need batteries, at least in our current paradigm. In kind of my own time, I'm also interested in using machine learning algorithms to do material discovery and material prediction. The big thing is that our traditional way of doing materials chemistry or materials science is that we kind of do this dharmic cycle of trial and error, where you have an idea, you give it a shot, you go to the lab, you make it. That actually takes a long time usually to make it, and then characterize it and really figure out what you've made. And often it doesn't actually lead to what you want, because we are clever, but of course nature is actually really complicated. And so what these machine learning models can help us do is actually break outside this box, because we're biased by our previous information and knowledge. So one of the things that we did recently was actually use some of these machine learning models to try and predict the properties of thermoelectric materials. So a thermoelectric device is actually just a really simple way to generate electricity. It's a phenomenon in the same way that a solar cell, if you shine light on it, it generates electricity. A thermoelectric, you can either apply a temperature difference and generate electricity, or you can actually put in electricity and generate a temperature difference. So people are really interested in doing this because it is very scalable. You can make it any size you want. You can hook more of them together if you need more voltage or more power. And the other thing is there's no moving parts. And so you can make it very small. So nowadays, actually, some kind of more niche applications, people are using them for drink coolers in some of the more higher-end luxury cars, and also for seat coolers and seat heaters and things like that for climate control. So these are a kind of a really exotic class of materials. They've been around for 200 years. But if you look at the Moore's law for computers, of course, the number of transistors doubles very frequently, although that's no longer happening. If you look at how long it takes to double the performance of a thermoelectric device, the Moore's law is about 100 years. And so over the past 10 years, it's actually been quite rapidly improving. But we're trying to figure out new ways that we can break out of the existing space. So with some collaborators, we developed machine learning models to actually predict the properties of some of these materials, so that we don't have to go make them and then test them, and both of those steps actually take a lot of time. And so what that did is it gave us a couple suggestions, some of which actually we thought some of those suggestions we thought were rather unique and quite strange and really counterintuitive. What we then found out actually was that when we kind of said, oh, well, that's strange, why would it suggest that? Let's look more into that. And is it just that our models are poor, or is there something kind of deeper to it? Because, of course, our knee-jerk reaction to things isn't always the correct reaction. And so if you then go and you look at this one particular material that was suggested, it turns out actually that it is very different. So the composition, what it's made of, is very different from known thermoelectric materials. So we're not just predicting a good material in the middle of good materials. That's not terribly exciting. We can probably do that without machine learning models. What's exciting about it is that just based on the composition, we're predicting something that's very different, and something that certainly we wouldn't expect. And what's even more interesting is that the crystal structure, or the way the atoms are arranged, is very similar to very good thermoelectrics that people have been studying. So even though we put no structural info into the models, it suggests this really exotic arrangement of atoms that's actually very familiar to workers in the field. So that's really exciting, because it can tell us that, oh, actually, here's something no one has thought of, but is actually worth looking at. Can I have some ridiculous hop? So I really like music and dancing, and so I do swing dancing, like Lindy Hop and Balboa, and I also sing barbershop a cappella harmony. So I meet with a bunch of dudes, and we sing down in Abingdon. So I don't know. I mean, like it's just kind of fun.